Okay. So we're up to the last chapter that we're going to cover in the class today, which is spherical trig. Hopefully you're noticing in the lectures that you guys are doing. So we have finished kind of medieval kind of math, and I guess the take-home lesson there, I hope you're seeing, is that like the math that was happening in medieval Europe is, it was behind what was happening in the Islamic Empire. It was behind what was happening in India. It was behind what was happening in China. But now, like in a rush at the end of the class, we're getting to the Renaissance, and in the next two sets of lectures that you guys are doing, we're kind of looking at European Renaissance maths, and all of a sudden, big things are happening. I think this week we're looking at Renaissance algebra, and so the big things there is the solution of the cubic, which is kind of like, it was like a big problem that that had been wanted for millennia. Ever since they solved the quadratic, what do we do with a cubic? That finally gets resolved in Italy in the 16th century. As well, at the same time, we're going to be seeing improvements in notation. So various things get invented, like the plus sign, the equal sign, all the kind of the use of variables. That's kind of happened before, but it sort of becomes much more mainstream now. The development of, that's going to be the following week, the development of logarithms. So really efficient ways of doing sort of computation. And then I think the following week, we're going to look at various realms of mathematical science, like logarithms, like astronomy, mechanics, geography, navigation, that sort of kind of thing. And we'll kind of see that Europe kind of takes its place as kind of a leader in the mathematical world. Whereas before we've seen, someone like Al-Kashi, who was in Samarkand in like around 1400, he would have been, he's the leading mathematician in the world. And then sort of after that, we're going to see development of European names, eventually leading, of course, up to Newton, who we're all supposed to bow down to in some regards. Okay, so let's talk. I'll talk more about that next class after you've had a chance to have a look at some of the lectures that you guys have been doing. So as I said, the last chapter we're going to look at is the chapter on spherical trigonometry. Oops, what happens here? It doesn't want to. No, there we go. So spherics. Okay, so one thing that we kind of know is that looking at the sky and doing some kind of astronomy is really common to sort of all cultures. So has anyone been to Cahokia near St. Louis? Yeah, and that's pretty much, it's got kind of like things there that was obviously meant for observing the sun where it rose. There's kind of like a Stonehenge. It was made out of wood, but yeah, it was kind of there. The Stonehenge itself, you look at all kind of cultures, and they've got stories about the sky. Sort of constellations seems to be a fairly common concept. They have stories about constellations, and this is important because they know that when certain constellations appear, it's time to plant crops or whatever. The Egyptians were interested in, I think, Sirius, the star Sirius, because when that was at a certain point, that was associated with when the Nile started to flood, all these kinds of things. So astronomy, the earliest kind of astronomy is really some kind of timekeeping. And so timekeeping, I mean, in the broad sense, you know, like it could be, you know, where in the year you are, you know, what season is it, but also timekeeping, you know, like, you know, what part of the day is it? And so when we talk about spherics, there's two spheres that are kind of interest of us. And that's the celestial sphere, and that's the one we use when we're doing astronomy. So what we're basically thinking about is, you know, we've got the Earth, around it there's this sphere, and it's got the stars on it, and the planets and the sun and the moon travel along that sphere. The the universe is finite, but it's at a great distance, so that the radius of the Earth is insignificant when compared to the size of the universe. And then the other sphere, of course, is the Earth, and you study that when you're doing geography. So the Babylonians definitely talked about a celestial sphere, because, you know, from them we get the zodiac. Well, the Greeks got the zodiac from there. So the idea, so zodiac is Greek for belt. It comes from the Greek word for belt, and it's kind of like this band of constellations where the sun travels through. Okay, and so the Babylonians kept note of, you know, stars when they rose and fell, the planets, the position of the planets, position of the sun, the moon, eclipses, that kind of thing. So for that, they had to have some kind of way of measuring things. So that's where we get angle from, the whole idea of degrees. Like there's 360 degrees in a circle, comes from the Babylonians. But it's really the Greeks who really kind of advanced kind of an idea of doing some kind of spherical geometry, some kind of spherical trigonometry. The Indian, we've already seen that Hipparchus, the work of Hipparchus had been sent to India with Alexander the Great, and so they developed the trigonometry, but they didn't really develop that much spherical trigonometry. And from India, we know it went to China in the Tang dynasty. But the Chinese, as I've said before, were very strong at calculating things. You know, their algebra was very, very strong. But they didn't really start looking at spherical trigonometry till the Song dynasty, which is around 1000 to 1200, I believe. Okay, so it's really the Greeks who kind of developed spherical trigonometry, and then it's the same old story. It goes, the Islamic mathematicians pick up this thing and then develop it, and then it goes from there, it heads to the West. So that's a story that we've already seen with algebra, with arithmetic, and with normal trigonometry. So what are we calculating when we do spherical trigonometry? So if you think about what's the basic thing that you do in trig, it's angles and lengths, right? So you've got a triangle, you want to know the side of a triangle, you want to know the angle that a triangle makes, okay? So we're going to have angles between lines, so we've got to figure out what do we mean by lines when we talk about a sphere. And lengths, what do we mean by kind of lengths? How are we going to measure lengths? So usually we're going to measure lengths in distance, but on a sphere, well, should go ahead a little bit. By lines, we mean great circles. So a great circle is when we take a sphere, and you cut it with a plane and you go through the center of the sphere. So those great circles are what we mean by straight lines on a sphere. And it kind of does what we want a straight line to do. So if I want to go from Kirksville and I want to fly to New York, right, I figure out the great circle that goes between New York, Kirksville, you know, and that plane in the center of the Earth. So that's 3 points, that makes a plane. I cut, and then I follow that great circle, and that is actually the shortest path that we can go from here to there. Okay, so it really is the shortest distance. So it does what a straight line is supposed to do. Okay, and so that's what I mean by angles between lines. So we'll talk a little bit about how you would measure those kind of angles. And lengths, well, if you think about it, because we're dealing with circles here, all distances can be angles, right? So, so if I've got a circle here, and you know, here's Kirksville, and here's New York, and I'm going to go from here to here, we can measure that as in miles between it. But if we go to our great circle, here there is an angle that we have on our great circle. So this angle here measures perfectly that distance there. So all distances can be measured in terms of angles. Well, it's arcs. All distances, everything can be measured in terms of arcs, and arcs and angles are the same thing when you do it like that. So in one point, that's a kind of simplification that you find in spherical trig. So on one hand, it seems harder because it's just different and you haven't seen it before. But in the other hand, everything is just angles. So that's something to remember. Other important things are parallel circles. So that's if you take a plane and cut through a sphere and don't go through the center, you get what's called a parallel circle. So important example of those are the parallels of latitude. Okay, so the equator is a great circle. And then if we look at all the cuts parallel to the equator, that gives you latitude. And that's true for any great circle. It's got corresponding latitude parallels of latitude. Other important examples are the meridians of longitude. They're also great circles. When we talk about the celestial sphere, there's a couple of really important great circles. So there's the celestial equator. And so that's like if we take the equator of the Earth and just, you know, take that plane and shoot it off to infinity and beyond, so that, well, not to infinity, but to a great distance, so it hits the celestial sphere, we get the celestial equator. So the celestial equator lies directly above the equator. Okay, and it's, you know, all to do with the Earth. Well, we know it's to do with the Earth spinning round and round and round, right? Another important great circle is the ecliptic, which is the great circle that the sun maps out as it goes around the celestial sphere. And the zodiac, the belt, is the belt around the ecliptic. Okay? And so with the celestial equator and the ecliptic, they're kind of like equators, and you can put like a coordinate system. So for these two things, we've got like north and south poles. So there's kind of like two north poles. There's the North Pole which it comes from the North Pole on the Earth. So we go from the center of the Earth up to the North Pole. We go up, and when we hit the celestial sphere, we get the celestial North Pole. But there's also the North Pole that comes from the ecliptic. I forget what they call that. It's the blah, blah, blah North Pole. And of course, you get a South Pole as well. The other important great circle is the horizon. And so that's with you as the center. So where you are, you have an horizon. So you go out sort of horizontally, you got a great circle there. And then above that, you've got the zenith. Yes, it's the zenith. And down there, you've got the nadir. And that's your own personal coordinate system that you have, sort of based upon where you are. Okay. So as I said, the Greeks sort of started like treating this kind of like a geometry. And the first person is Autolycos, I guess, around the 4th century BC, and he came up with some quite rudimentary results. So any two great circles bisect each other. Okay. Given any two diametrically opposed points, so given any two antipodal points, if you look at all the great circles that go through those 2 points, okay, so if you take any 2 points on a sphere, usually there'll be a unique straight line joining them, unless those 2 points are at poles, in which case there's infinitely many straight lines that go through them. So it's a very strange kind of geometry. And if you look at all those great circles, there's going to be then a unique great circle which is perpendicular to the great circle, all the great circles that you've done. So basically, any two antipodal points can be turned into poles. And you look at all the great circles going through those can be considered meridians of longitude for those poles that you've chosen. And for any two poles, there's a unique equator that splits everything in half. So that's this converse here. Conversely, given any great circle, so you can be given two antipodal points, and then you can construct like a longitude and latitude system from that, or given any great circle, that can be an equator, which you can then build into a latitude and longitude system. And then we can measure angles between two great circles, right? So given any two great circles, you know they have to intersect at 2 points A and B. Those A and B is going to be poles, and you're going to have an angle here that you can say is the angle between those two great circles. So anything has between any two great circles, you have an angle between them. Okay. So that's kind of like the basic. The first person to really come up with some kind of trig is Menelaos, and he wrote a book called Spherica around 100 AD. Okay, so this didn't go to India, right? So this is later, so this is well after Alexander the Great, so it kind of just stayed in Greece. And he was the first one to consider spherical triangles. And spherical triangle is just area enclosed by the arcs of three great circles, each arc being less than a semicircle. Okay, so if great circles are straight lines, then if you have three straight lines, you have a triangle. And so he did And he came up with a theorem. And so you've got this sort of configuration. So you have a couple of, you have three great circles like that. And then there is, he proved there's some relationship then between the chords of the arcs there. And we notice that it's a chord of 2 times the arc. And so straight away we know that, well, instead of looking at chord of 2 theta, we should just really be looking at sine of theta. And so this is what we have here. And so notice this is a relationship just about arcs, right? So it's about kind of about lengths, and we're taking sine of lengths. And the reason why we can take sine of lengths is because lengths can be thought of as angles. And so we get this. There was another identity there that I forgot to put on. So this one was this one. There's a corresponding one for that one. And later writers developed more of these kind of sort of situations. They came up with more kind of trig identities. And the thing about spherical trig identities is everything gets hit with a trig function, right? So there's no, I'll show you what Pythagoras' theorem is later in spherical geometry, but everything gets hit with a trig function. It's cos or sine or tan of something is involved in it. Okay, and so the person who really advanced this was Ptolemy. So he was like a generation after Menelaos, and he used Menelaos' theorem to solve right triangles, spherical right triangles. And he did it using this double Menelaos configuration. So you're given this right triangle ABC, right? And you construct that, you look at these arcs here. So PM is an equator to A, and QN is an equator to B. And you fill it in, and then you have these Menelaos configurations, and then you just apply these results here to the configuration you've got there. And we see we get these kind of nice trigger identities here. I don't really want to go into all the details because it gets nicely simplified in the next slide. So we have these things here. Notice, because we use this to be an equator to the pole, we get these 90 minus, right? So we know that these are actually cosines. And when the dust settles, right, this is cosine divided by sine, which is what? That's a cotangent, isn't it? Sine of 90 is 1. This is a cosine of little a divided by sine. So that's a cotangent of little a. And so if you go ahead and rearrange things, you get tan of A equals tan of little a over sine of little b. And this is what I mean when I say that all trig identities, spherical trig identities, look like regular trig identities, but they get trigified, okay? So look at this. This is a right triangle. This is the angle A. What is tan of A in regular plane trigonometry? Opposite over tangent. It's A over B, right? So in regular world, tan of A is A over B. In spherical world, it's tan A over sine B. So that's what I mean. Everything gets, there's a trig function thrown into all your identities. Here is sine of A, right? Sine of A, we know, is A over C. Well, in spherical trig, sine of A is sine of A over sine of C. The third identity is that cosine of B is tan of little a over tan of little c, right? Well, that's, we know cosine of B is adjacent over hypotenuse. Again, you see adjacent over hypotenuse, but they get hit by a tan. And this is the Pythagoras theorem for spherical trig. And there's a standard trick to make it look like the regular Pythagoras theorem. What's the power series for cosine of C? What's the first two terms in the power series of cosine of C? Cosine is an even function.
So isn't it like 1 over 2 factorial?
Right, there's no C term, right, because it's an even function. There's a C squared. Does anyone know what the coefficient of C squared is? What do we divide by? Oh, this is so hard. Calc 2. 2 factorial, yep. Plus higher terms. Cosine of A is 1 plus A squared over 2 factorial plus higher terms. 1 plus, this is for cosine of B. So it's saying that 1 plus C squared over 2 equals 1 plus A squared over 2 plus higher terms times 1 plus B squared over 2 plus higher terms. Okay, 1 times 1 plus A squared over 2 plus B squared over 2. Plus higher terms. Get rid of the 1. Get rid of the higher terms. Multiply by 2. We get C squared equals A squared plus B squared. So we actually, so this is saying that if we make our sphere big enough, we kind of blow it up so it becomes flatter and flatter. In the limit, this becomes the Pythagoras theorem. Okay, just to show you that. Yeah.
Okay, so so trig tells us that we can only take like sine, cosine, tangent of angles. So why is it taking it of side lengths?
Because side lengths can be thought of as angles because they are great circles. Oh, so it's in the following thing here. Oh, no. Here. So any two great circles, when they meet, there's going to be an angle. So we think then of the distance between these 2 points as that angle. It's the same, we can think of distance as an angle because it's on a sphere. It's on a circle. So when we look at this distance here, it corresponds to an angle there. So we can just take the angle to be the distance.
Okay, and this is like before they found out that arc length was radius times the angle.
Radius. Yes. So before angle, they just thought in terms of arc length. So for them, actually, trig was a function of arc length.
Oh, okay.
And it's only in modern times that we say arc. Well, arc length and angle are the same thing, sort of thing, like if you take your circle. Okay, and so that's the kind of the hard bit of spherical trigonometry, is just, but the thing is you have trig identities, and you just do stuff with trig identities. Just like in normal plane trigonometry, you use those trig identities. Here you've just got a whole different bunch of trig identities, and that's how you do things. And so one of the things that the medieval Islamic mathematicians did was they came up with a whole lot more of these scenarios. And I think they found like 72 different cases. And so they all lead to trig identities, which are the same as our trig identities, except they're being trigified, as I like to say, like that. Okay, so that means you can solve, but using this, you can solve triangles just like you can solve, so it's exactly the same as in normal trig, you are solving triangles. So let's have a look at some examples. Where is the sun? Okay, so this is the problem of declination and right ascension of the sun. Right, so latitude and celestial longitude and latitude are based on the ecliptic. If you use the equator, the latitude and longitude is called declination and right ascension. Okay, so here is a problem. Okay, so remember the sun is traveling along the ecliptic. So this is V, this is the vernal equinox. So longitude of the sun corresponds to what day of the year it is. If you think about it, right? If the sun is at V, that means it's March 20th. Okay? If we're at 30 degrees, right? 30 degrees is 1/12 of a circle. 30 degrees means it's 1 month later. And so we go from Aries to Taurus. Does that sound right? Is Taurus after Aries? Yeah. So this is the point in which we've got where the sun is in Taurus. So, I mean, they all knew where the sun was, right? Because they saw that, you know, when the sun goes down, suddenly the stars appear, and there would be Taurus, where the sun had gone down. And when they look up in the morning, when the sun's about to rise, Taurus is there just before the sun appears. So they know where the sun is. Okay, so this longitude measures out the year as it goes from 0 to 360, as it goes from March 20th to March 20th. So the sun is here. Where is it then in the equatorial system? What are its coordinates? Okay, well, we've got a right triangle. We've got a right triangle. We know this length here, that's the longitude. We know this angle here. That is the angle between the ecliptic and the equator, which is 23.5 degrees. We want to find alpha and delta. We want to solve this right triangle. Okay, well, that's quite easy because we just look at the equations we had before. We just, you know, from equation 2 that I had before, we see that sine epsilon is sine delta divided by sine lambda, And from equation 3, we have cosine epsilon equals tan of alpha, tan lambda. We're given what lambda is. We know what epsilon is, so we can solve for alpha and delta. And so we go ahead and just do that. I use 30 degrees, right, because tan of 30 degrees is a half, and tan of 30 degrees is 1 on square root of 3. So you see what I talked about before with this need for auxiliary tables? Because if you think about it, you're going to be looking up sine or cosine of 23.5 degrees all the time. Right? You're going to have a regular table where lambda goes through, 1, 2, 3, 4. So you can figure out where the sun is at any given time. You're going to then have a table of alpha and deltas for every day of the year, basically, because every degree basically corresponds to a day. Okay. And so when this is 30 degrees, this is 11.5 degrees, and this is 27 degrees, 54 minutes. That's where the sun is. You know where the sun is in the celestial sphere. Now, an important thing is that spherical triangles add up to more than 180 degrees. Did people know this already? Some of you knew that already? Okay. And in fact, the number of degrees in a triangle tells you how big the triangle is. So triangles with the same angle measure have the same area. So you can actually use angle. Not only can you use angle to measure length, but you can use angle to measure area, which is like a kind of weird thing. Right? So the excess here measures the area of the triangle. And so let's just find that. So when we're trying to figure out h, we use another one of those identities. We find it 69 degrees, 22 minutes. And so the total angle is 192 degrees, 52 minutes. So this triangle has angular excess of 12 degrees and 52 minutes. And so you can actually go ahead and you can do stuff with that. So this is actually a pretty straightforward problem. Okay, so as you go along, as the sun goes along, forms this right triangle, and you can solve that right triangle just by using those formulas. So you have a table for that. Let's do something a little harder. Rising time. Okay, so time is measured by the motion of the equator around its axis, right? So the Earth has an equator, and the Earth spins once in 24 hours. So 24 hours corresponds to 360 degrees. So 15 degrees means 1 hour, and 1 degree is around 4 minutes. So this is actually how you can accurately measure time. Is if you know what your longitude is, you can then measure when it's noon. You know when it's noon is because that's when the sun is at its highest point. So you say, okay, this is noon now. I'm at 15 degrees. Okay, so that means, and say I've got a clock that's measured to like Greenwich. And so I can see when it's noon here locally, and I can figure out when it's noon at Greenwich. I can figure out where I am. So I can solve longitude. Longitude is a time problem. And this is how the explorers, it's a big thing. Has anyone read that book, Longitude, by Sobel? It's a really great book. It's all about the early problems of navigation and solving the problem of your longitude. Okay, so we've got our three great circles. We've got the ecliptic, which is where the sun is going around. We've got the equator, and then we've got our horizon, what we're actually seeing, right? And so here, this must be sunrise, I think. This is why it's called the rising time, because this is where the ecliptic, it's the rising. So if the sun is there, the sun is rising where we are at right now. Okay, so the problem is at a given latitude, determine the rising time, which is this length here, right? This is how much the equator is above the horizon. And so that's going to be a function of this distance here, the ecliptic from the horizon, and phi, which is your latitude. Okay. So let's solve this for Kirksville. At Kirksville, we're at 40 degrees 12 minutes north. And let's give the longitude at 30 degrees, so it's around April 19th. I should have actually figured out what today's date was and turned that into longitude. Okay, so we know what delta and alpha are from the previous slide. Okay, and so we use an equation where, so here, this here is the latitude, and we know delta from before, so we're going to figure out sigma, which is this little thing here, EC. So we figure out EC, we figure out that's 9 degrees 54 minutes, and so VE is this minus delta, it's 18 degrees. So 18 degrees corresponds to around an hour and 45 minutes. Okay, what can we use that for? Well, let's figure out what the length of day is then on April 19th. Okay, now if the sun is rising at lambda, it's setting at lambda plus 180. So to find the length of day, we just subtract the rising time of lambda from the rising time of lambda plus 180. So this gives us this equation here, but alpha of lambda, but so we've got sort of like two triangles like here, but they're like 180 degrees placed from each other, and where one is down, the other is up. So this minus this is just 180, and this is just minus of that. So we do that. So we go back here, we figured out what delta was, or what sigma was. So when around April 19th, the length of day is 199 degrees and 48 minutes. And that corresponds to 13 hours and 19 minutes. And we can also calculate where the sun's going to be when it rises, right? Because that's just going to be the length here of that arc EH. And so we use one of those equations, and we find that it's 15 degrees 8 minutes. So on April 19th, the sun will rise at 5:20, right? Because if the day is 13 hours and 19 minutes long, at local time, noon is always the midpoint. So I just take 13 hours and 19 minutes, I halve it. That's how much the morning is. So what's that? That's 6 hours and 40 minutes. So the sun rises 6 hours and 40 minutes before noon, so that's why it's 5:20. And it's local time, right? So that's Kirksville time, which no longer exists, of course, because we've switched to central time. And it's going to rise at a point 15 degrees 8 minutes north of the east point of the horizon. So when I actually looked it up, it rose at 6:25 a.m. on April 19th, which in local time is 5:16. So I don't know how I got the 4-minute error. Maybe rounding error. Also the fact, of course, that it's not really uniform motion, right? Because we know from Kepler's laws that the sun, the Earth moves quicker when it's closer to the sun, that kind of stuff. But that's good enough. Yeah. So that's actually pretty amazing. So like we went from this problem, which I think is not really that exciting, right? To actually figuring out something that, sea captains are supposed to do, that sort of stuff. Anyway. What do you think? Okay, let's stop there.